Right. So we were doing the last exercise in the transformation homework, and we saw that this one was a reflection in the y-axis and then a shift to the left by 2. So you flip it over. Sorry, a reflection in the x-axis. I said that wrong. Reflection in the x-axis, right? Because we replaced y by negative y. And then shift it over 2 to the left. This one was, again, a flip, but this time a flip across the y-axis, right? Replace x by negative x, that reflects in the y-axis, and then shift up 2. So flip it over and shift it up 2. This one, we're going to have just a vertical compression. So this one is going to change shape, right? Can I get rid of this? Yeah, I can. And then maybe zoom in a little bit on this. Okay, does that help a little? Tends to be a little small, right? Okay, so if you replace y by 3y, then you'll have to divide by 3 to get, but that's then going to mean that y is 1/3 of what it used to be, right? Of course, 1/3 of 0 is still 0. So that point, so we're now compressing by a factor of 3 towards the x-axis. So what was above is going to be crunched down. What was below is going to be crunched up. Everything pushing towards the x-axis, right? So this point that was here at negative 1,3 is now at negative 1,1, right? 1/3 of the y coordinate. And this point here that was at 4, negative 3 is now at 4, negative 1. And we are done, right? That's all it is. It's just that one compression. Notice it's a different shape now, right? So the expansion and compression actually changes the shape. So here we're going to stretch vertically by a factor of 2. Again, the stuff on the axis stays there, but this thing that's at negative 1,4 is now going to be at negative 1,8, right? Twice as big. And this thing, which was at 4, negative 2, is now at 4, negative 4. Right? So pulling away from the x-axis. And that's it. Okay, all of them are good? Great. Any questions about that before we leave it? Any other questions? That's a good one, right? Yeah, it's kind of, you can expect some stuff like that on the exam probably, right? Which will be sometime next week, because we are just about done with chapter 2. So we can review tomorrow, maybe review on Monday again, and then test on Tuesday. How would that be? Gladly test you Tuesday for a hamburger today. Okay. And Jedzia, did I get your attendance? I'm not sure I did. Obviously you're here because you requested. Yeah. Okay. So let's go back to the book. And in the book, we see an application to business. Business? They do math and business? Maybe they do. Well, let's see, what are they talking about? A print shop. Oh, it's a business. Makes bumper stickers for election campaigns. Oh, they're probably hot off the press today. Yeah. How's your mailbox doing? Well, there's nothing in on Monday, right? Christopher Columbus. And yeah, but apparently there's a lot of issues. Proposition 14 and Proposition whatever, I don't know. I tried to read through some of them. It's pretty dense stuff. They want to have bond issues, right? Oh, there's some more math. Neither a lender nor a borrower be, I think is what the Lord said. But yeah, our elected officials ignore that because they want to borrow money from the banks to do good things for you. Yes. A print shop makes bumper stickers for election campaigns. If X stickers are ordered here X can't be 10,000 or more. Then the price per bumper sticker is 15 cents, right? That's what this represents. And then take away this tiny fraction of X dollars. What is that? This is the thousands place, 10,000, 100. That's a millionth. That's 2/millionth of X. Apparently, they make a lot of stickers. So you get some efficiency through large quantities, but only if they're really large, right? The total cost of producing the order is then 0.095x, so 9.5 cents per bumper sticker. Then take away the square of, is that 5? So this is the thousands, 10,000, 100,000. This is 5 10/millionths of X squared. Oh, well, let's write that on our paper because I'm having a hard time wrapping my head around all this, right? So we're going to say let X equal the number of stickers ordered. So this is 2.7, I think. Number 70, I think it's 2.7. Number 75. So we're going to say let X equal. These are magic math words. This is how you introduce a variable and just define what it means, right? So the number of, can I use the octothorpe to represent a number, the word number? You may be wondering, what's an octothorpe? Did we mention that before? This is an octothorpe. I love that word. Okay, so number of bumper stickers produced. Okay. Can I shift this over a little bit? Yeah. Then they say, so the domain is of X is, well, you could make 0, right? But you can't make 10,000 or more, right? So we're going to say that X is some number between 0 and 10,000, not including the number 10,000. That's what they say in the problem. Then the price, per bumper sticker, I'll just say per sticker, is defined to be, is modeled by, maybe I should say, this 15 cents per sticker, take away, a little efficiency factor where we got tenths, hundredths, thousandths, 10,000, 100,000s, 2/millionths of X. Dollars. So this is the price in dollars. And the total cost of producing the order price per bumper sticker and the total cost of producing the order. I'm not quite sure if that follows. Total cost of the order is, this is just something they tell us, right? So that's going to be 0.095x. X is the number of bumper stickers produced, minus, here we got tenths, hundredths, thousands, 10,000ths, 100,000ths, millionths, and finally in the 10/millionths place, there's a 5. And we got X squared, okay? You would think that you would multiply the price per bumper sticker by the number of bumper stickers produced and get the total cost that way. There must be other costs involved, right? Labor, maybe. and that's not included in the actual cost of the sticker, right? So there's the design of the sticker, there's who knows, right? So, but we'll just accept that this is the model, all right? So they say that revenue, when you're in business, this will be a familiar thing to you, right? Revenue is equal to the price per item times the number of items sold. And that's kind of what I was saying, right? Times number of items sold, which is X. Oh, no, this is the number of bumper stickers produced, I guess. So is that the same? Do we sell them all? I don't know. The revenue from an order of X stickers as a product of two functions of X. All right, let's see if X stickers are ordered. Somebody was complaining yesterday that we just shouldn't do applications. Oh, yeah. Okay, a couple of people are chiming in that they're here. Okay, I'll see to that. So X stickers are ordered. Then the price per bumper sticker is given by this first expression, and the total cost of producing the order is given by the second expression, and the revenue is given by this so express the revenue from an order of X stickers as a function, as a product of two functions of X. Price per item, which we know the price per item. Yeah, I think, so I'm going to say revenue, R of X, is going to be, here's the price per item, right? 0.15 minus 0.12345, counting the number of zeros, right? Times X. I'm just going to say we sell them all, right? X stickers are ordered, right? So yeah, if they're ordered, yeah. So this is the number of bumper stickers ordered, right? And so if they're ordered, that means we sold them, right? So the number of bumper stickers sold is X. And I guess, so this is a product of two functions, I guess. I mean, the second one is just X. So do we want to multiply that out? Let's not say we did, or we could. Okay, so now if I go back to the text, because I don't think we're done reading that, huh? Yeah, okay, so we did that first part, but there's a second part. And number 76 says, use the fact that profit is revenue minus cost. All right, so the money you bring in, take away what it costs you to bring that in. All right, so we have the revenue here and we have the cost here. So we're going to take the difference of those functions, and let's go ahead and distribute this, right? So we'll have 0.15, is this visible? No. 0.15x, right? Because we're distributing this x over these two terms here. Minus 0. There's a lot of zeros here. X squared, and then the cost is up here as 0.095x minus, I'm going to say 5 times 10 to the 1, 2, 3, 4, 5, 6, negative 7 x squared. This is 10 to the negative 6, right? I went to scientific notation because I couldn't fit in all those zeros. And so now we got some like terms to combine, right? Okay, so 0.15 take away 0.095. I have to use, I have to write that down because notoriously bad at arithmetic. Yeah, that's going to work, right? Yeah. I had it back in to check, and you see that works out. So this is 0.055, 55 thousandths x. And how about here, where we've got a negative 2 millionths, add 5 10 millionths, right? Add because it's double negative, right? So, you take the smaller quantity away from the larger quantity in magnitude and then assign it the sign of the, so it's going to be negative, right? But can I say this is 20 times 10 to the negative seventh? So 20 times 10 to the negative seventh negative plus 5 times 10 to the negative seventh. It turns out this is more of an arithmetic problem than anything else, isn't it? So take the smaller away from the larger and give it the sign of the larger. So that's going to be negative 15 times 10 to the negative seventh, okay? Yeah, that makes sense, right? So if you wanted to write that in terms of decimals, you'd write 1, 2, 3, 4, 5, 1, 5 x squared. So there's your profit. And I guess we're done, right? That was it. Okay. There are a bunch more of these things, is that right? Airplane trajectory in 82. Let's look at 82, then we'll move on to inverse functions. An airplane is flying at a speed. I'm sort of monitoring the chat, so if you have questions, just blurt them out or, yeah. I sort of imagine you, some of you anyway, with sort of all your family is around you, right? With siblings beating on drums and shouting at each other and doing the dishes, and that's why you're muted, right? But go ahead, just unmute and call out your question if you got one. All right, so what do we got? Airplane. Shall we read it on the? I suppose we ought. So that's here. An airplane is flying at a speed of 350 miles an hour. I think that's reasonable. At an altitude of 1 mile. Again, not unusual. Plane passes directly above a radar station at time t equals 0. Express the distance s in miles between the plane and the radar station as a function of the horizontal distance d in miles. Here they're defining a variable d as the distance horizontally that the plane has flown. Then express d as a function of the time. Yeah, well, this is kind of like that ship passing the lighthouse, right? We talked about that yesterday. So let's draw a picture of what's going on. And so this is number 82. By the way, we could have done a little bit more analysis on this. What do businesses want to do? They want to maximize their profit, right? Is that possible here? Well, sure. Here the profit goes as a parabola. And which way does the parabola open? Downwards, right? Because why? Well, the coefficient of x squared is negative, right? So that's a downward opening parabola. And where's the vertex? Well, h is negative b over 2a. So that's going to be 15 10 millionths divided by 55 thousandths. And so that's going to be, I'm going to multiply by 1,000 on the top and the bottom. So if I do that, I'm going to move the decimal point over 3 places. Yeah. And so I'm going to write 0.0015 divided by 55. Doesn't make a lot of sense, does it? You're making less than one bumper sticker then. Yeah, don't make any bumper stickers. Wait, am I doing that right? Negative b over 2. Oh, I have it upside down. No wonder. Yeah, negative b is 0.055 over 2a. Oh, and that's 2a, right? So this is going to be, in fact, um, um, 0.0003. Oh, and it's going to be 55 divided by that, right? So negative b over 2a. Okay. Sorry, because it's in ascending powers instead of descending powers, and yeah. So a is this negative 0.00015, and b is 0.055, right? And so I don't know, that doesn't go in evenly. I guess we'd multiply by 10,000. And so we have 550,000 divided by 3. Yeah, so that's going to be over 100,000 bumper stickers. Somewhere in there is going to be your maximum profit. Anyway, we're back to, so here's a radar station. And here's a 1 mile height. And the plane is here at time 0 and is traveling a distance d horizontally. This is a right angle because it's directly overhead. Sorry, radar station is here. And so in part A, they ask, express the distance s. So this is the distance s. So we'd like to express that from the radar station to the plane. Here's the plane. Right, the plane is traveling this way at an altitude of 1 mile. And so we've got a right triangle here, right? Right. It's not a left triangle, it's a right triangle. And how we doing? We've got then Pythagoras' theorem kicks in, right? So the sum of the squares of the legs of a right triangle is equal to the square on the hypotenuse. I mean the hypotenuse. So that gives us, you know, the legs are 1 and d, the hypotenuse is s, so 1 squared plus d squared is s squared, according to Pythagoras. And should we write Pythagoras here? It's an AS at the end, right? Pythagoras. Then we get S is the positive square root of 1 plus d squared. Well, what's d? Well, they tell us that the plane is traveling at a speed of 350 miles per hour. So let t equal the hours, since the plane was directly overhead. Directly above, can I fit in the word above here? Yeah, directly above the radar station. Then d is going to be speed times time, right? And the speed is 350 miles per hour, and the time is t. So we see that d is a function of t. If we substitute, you know, so we can get s as a function of t by substituting for d, and that's like a composite function. In fact, it is a composite. So I've got s of d is this, s of d of t, right? Which we could also just sort of denote as s of t is positive square root of 1 plus, I'm not going to square the 350, I'm just going to put it in, I'm not going to compute the square of 350, I'm going to indicate that it's being squared using parentheses, and we're done. Questions about that, or? Yeah, I mean, I think we're done. Was there something else? Use the yeah, to express S as a function of T. Right, that's what they wanted us to do. Oh, and they drew the picture for us. Okay, very nice. Oh, they got a little thing on compound interest here. Yeah. Compositions of even and odd functions. So suppose that G is even and H is F of G. Is H necessarily even? Mm-hmm. So this is number, and we will do inverse functions next. But this is kind of an interesting question. If G is even, is H equals F of G of X even? That's our question. Well, in other words, is H of negative X equal to H of X? Another way of asking the same question, right? That's what it means to be an even function. That's the definition of an even function. It's got y-axis symmetry. Well, yeah. H of negative X is going to be F of G of negative X, and that's F of G of negative X. But what do we know? We know that G is even, right? So G of negative X is just G of X. And so this is F of G of X, which is H of X. And that's what it means to be even. So yes, the answer is yes. How are we doing? Okay, so let's talk about inverse functions. I think we're ready, are we? Yeah, functions and their inverses. That's the next little bit here. And I guess I'll put this over here. So we're going to talk about what it means to be a one-to-one function. Then we can talk about the inverse of the function. Then we'll talk about how to find an inverse function. Then we'll talk about the graphs of functions and their inverses. And then maybe some applications. Because they're so much fun. And plus, what's this good for? Well, it's good for applications. It's good for just thinking about stuff too. But so what do they say here? The inverse, this is going to define inverse here, of a function is a rule that acts on the output of the function and produces the corresponding input. So the inverse undoes or reverses what the function has done. This is not always possible, right? In fact, there's a principle in physics called entropy that says that things tend to go from a state of higher order to a state of lower order. Things fall apart. The famous novel by Chinua Achebe, which I reread recently and was a little bit disappointed by it. It didn't seem that good after all, but it's a great title. I think actually the title comes from Yeats, The Center Cannot Hold. What's the name of that poem? It's escaping me now. I think it's Yeats. I would hate to misquote. So let's go out here to search for the poem. How about the falconer? Falcon cannot hear the falcon. That's sort of another quote from that poem. And it'll take us to the second coming. I had the poet right, William Butler Yeats. Yeah. Turning and turning in the widening gyre. Oh, that's very much a trigonometry idea. The falcon cannot hear the falconer. Things fall apart, Chinua Achebe. The center cannot hold. Mere anarchy is loosed upon the world. Hey, this is like an augur of today. The blood-dimmed tide is loosed, and everywhere the ceremony of innocence is drowned. The best lack all conviction, while the worst are full of passionate intensity. Yeah, okay. So it goes. How are we doing? Little poetry to sort of ease our segue into inverse functions. So what led me to that was entropy, which things fall apart. Sure, the center cannot hold, and right. So think about a soda machine, right? What's the input when you go to get a soda from the soda machine, right? It's a function, right? It's a machine. It has a function. What's its function? Its function is to take your money and your choice, which is a little bit tricky, right? Because you have to push, not only put in the money, but then push a button as to which soda do you want. By the way, don't drink that sugary water stuff, but that's another story. And then the output is the soda, right? So how would you reverse that process? Is it reversible? Well, actually, the soda machine is not set up to do that, right? It's not set up to take a soda, spit out the money that, you know, that soda costs, and then undo your selection somehow. I don't know how you would do that. So yeah, that's an example of a function that really doesn't have an inverse, right? So many functions don't have inverse, but many do. What kind of functions have inverses? One-to-one functions. All right. So what do we have here? Let's compare two functions f and g whose arrow diagrams are shown in figure 1. Okay, yeah, so this function is one-to-one because for each input there's exactly one output, right? No more, no less. Also, for each output, there's exactly one input that produces that output, right? So it's got to be both of those things are true. Actually, to be a function, for each input, there can be at most one output. But for a one-to-one function, for each output, there's only one input that can produce that output. So that then there's a one-to-one map between input and output. And you can see in this diagram, the first one on the left here, you could reverse this process and it'd be well defined, right? It would be a function. The mapping from B back to A, 10 would go to 4, 7 would go to 3, 4 would go to 2, and so on. With this one, this is not one-to-one because while it is a function, for each input there is at most one output. For this output 4, there are two different inputs that produce that output. So it's not one, it is a function, but it's not one-to-one. So here's the definition of a function. And this is kind of interesting logic. They have sort of the negation of the way I usually think of this. So they say a function with domain A is called one-to-one if no two elements of A have the same output or the same image, right? That is, if the outputs are different, the outputs are different whenever the inputs are different. Another way to say that is the outputs are the same if and only if the inputs are the same. You see that both of those work, right? Yeah, so that's that. They in fact they also make that point that another way of saying the same thing is that if the outputs are equal, then the inputs are equal. In fact, the outputs are equal if and only if the inputs are equal. Certainly, if the inputs are equal, then the outputs are equal because it's a function. But we can go further with a one-to-one function and say the outputs are equal. If the outputs are equal, then the inputs are equal. And so we know that a function satisfies a vertical line test, right? The vertical line will intersect the graph of a function at most once. For an inverse, for a one-to-one function, it also satisfies a horizontal line test, which is say that for each output, there's at most one input that produces that output. So every horizontal line will intersect the graph of a function at most once, right? Maybe not at all, is the subtext of that, right? Deciding whether or not it's one-to-one? So they start out with an example. Is f of x equal x cubed one-to-one? Well, if x1 is not equal to x2, then x1 cubed is not equal to x2 cubed. Two different numbers cannot have the same cube. Therefore, it's one-to-one. That's one way of doing it. The other way is to saying no horizontal line intersects the graph of x cubed more than once. So by the horizontal line test, it's one-to-one. Now go exercise 15. Oh, really? Let's just keep 15 in mind. That's one we want to do. Okay, so decide whether a function is one-to-one. Is g of x equal x squared one-to-one? Well, no, and here's an example of two different inputs that produce the same output, right? The square of 1 is the same as the square of -1. And also, if you like, this is a parabola, which doesn't satisfy the horizontal line test then, right? A horizontal line can intersect a parabola more than once. So do exercise 17, they say. So show that it is one-to-one. Well, you say, okay, the outputs are equal, and you write a sequence of equivalent equations at the conclusion of which you can say that the inputs are equal. So the outputs are equal if and only if the inputs are equal. Okay, so we say that if f of x equals y, then the input x produces the output y, right? Then the inverse function does the opposite, right? It takes that output y and produces the input x that f takes to y. So how do you find f inverse for specific values? Well, if you know that f of 1 equals 5, then you know that f inverse of 5 equals 1. It just reverses the process, right? Similarly, if f of 3 equals 7, then f inverse of 7 equals 3. And they show that the map going backwards, right? So finding values of an inverse function, a table of values, so you just reverse the table, right? So if you have an input-output table for a function, reverse the columns and you got an input-output table for the inverse function. So there's this nice property that if you take the composition of a function with its inverse, either way, right? Either f inverse of f or f of f inverse, then it's like you did nothing, right? Because the output you got the output, then you took the output back to the input, and you're where you started. So that's one way to verify that two functions are inverses, is to take their composition and show that their composition is just x. So how do you find the inverse of a one-to-one function? Well, they have a 3-step process, and you can skip step 2 if you like. Step 2 is not essential. In fact, I usually reverse steps 2 and 3 here. Am I following the chat? I'm not. The chat is obscured for some reason. Where's the chat? I don't know. Oh, here it is. Okay. There's nothing new in the chat. All right. Oh, in fact, they make this point that steps 2 and 3 can be reversed. And if you don't even do step 2, then you end up with a formula for the inverse function in terms of y, right? Instead of in terms of x. So why do that reversal at all? Well, there's maybe 2 reasons. One is that, we feel more comfortable with x being the input and y being the output. So if you have, f inverse of y equals x, well, you prefer to have f inverse of x equals y. So, but it's a different x and it's a different y, right? So, suppose the input of a function is cats and the output of a function is dogs, right? When you reverse x and y, does that mean cats become dogs and dogs become cats? No, cats are still cats. So if the function takes cats to dogs, then the inverse function takes dogs to cats. But that doesn't make a dog a cat. I hope that's perfectly clear. All right. So finding the inverse of a function. Okay, so here's an example of that process. So here's the function definition, right? Then you write the equation without the function notation. So no f of x, just the output variable y in terms of the input variable x, the formula, right? And then you solve that equation. Oh, do they reverse? They don't reverse. So they first solve for x in terms of y, and then they reverse the variables, which that's not an essential step. Oh, there's another reason for reversing the variables, which if you want to plot both the function and its inverse together on the same coordinate plane, if you didn't reverse the variables, you just, you know, be looking at the same curve, right? Because it describes the same relationship, except output going back to input. If you want to see them as separate curves, then reversing the variables accomplishes that as well, as we'll see, okay? So some rational functions are invertible. So here's an example of one that is, and you can see there's a fair amount of algebra here, right? So here's the function definition. You write that as an equation involving the variable y in terms of the variable x. And then you solve for x in terms of y. You can see, you know, you got to, use the multiplication property of equality, then distribute, then use the addition and subtraction properties of equality to get the terms involving the variable x together on one side and the terms not involving x on the other side, then factor out x from the terms involving x and divide by its coefficient. So in this case, you get a nice formula for the inverse function. Okay, so here's this nifty thing about the graphs. If you do reverse the variables, then plot both functions in the same xy coordinate plane, then you will see a symmetry. So notice that this function f is 1-to-1, right? It passes the horizontal line test. And that the inverse function is the reflection of that shape in the line y equals x. So if you were to fold the plane along this line y equals x, you would see these two curves overlapping. It is essential, if you're going to see that or do that, that you use the same scale for the x and y axes, right? Otherwise you'll get a distortion, and that will be different in the reflection. Okay, so are we ready for exercises? Applications? Yeah, well, we'll talk about applications when we get there. Let's get down into some. I think we want to do some exercises. So how about number 4? I think this is like a fill in the blank. We can just talk this one through, right? A graph of a function f is given. Does f have an inverse? If so, find f inverse of 1. Oh, all right. Is that, yeah, I guess, yeah. So f inverse of 1. Actually, this doesn't look like that, right? Because, oh, f of 3, can't tell where the axis, 1, 2, 3. Yeah, this is not that, because oh, maybe it is. So, yeah, if the output is 1, what input produces that output? Yeah, that's going to be 3, right? So f of 3 equals 1. Do you see that? If you go 1, 2, oh, f of 4, sorry. I was counting wrong, right? So here's 0, count over 1, 2, 3, 4. This is x equals 4. And then go up 1 unit, you're on the curve. So f of 4 equals 1. That means that f inverse of 1 equals 4. How about 3? 1, 2, 3. That's a little small. Oh, sorry. Yeah, so I think we'll go, if we go to 5. So count over 1, 2, 3, 4, 5. Then f of 5 is 3. That means that f inverse of 5, sorry, f inverse of 3 is 5. It's a house of mirrors, folks. It's easy to get lost. So these are a graph of a function f is given. Determine whether f is 1 to 1. Well, implicit here is that y is a function of x, okay? And so, which one of those show y as a function? Because, here in 8, you could also have x as a function of y, right? And here in 9, you can have x as a function of y. And that would be the inverse function, right? This doesn't satisfy the horizontal line test in 10, and 7 doesn't either, right? 12, yeah, that satisfies the horizontal line test. 11 doesn't. Okay, we got a bunch of one to determine whether the function is 1 to 1. And there's sort of a little rule of thumb, if you got an even term in a polynomial, it's not 1 to 1, generally speaking, right? Is that always true? I have to think about that. In number 18, though, that's 1 to 1, right? Yeah, I think yeah, I have to think about that to say if there's an even term. Finding values of an inverse function. Okay, so we talked about that a little bit. Let's move on to, we were going to talk about 15. Square root of x. Is this a 1 to 1 function? That one's not so obvious, huh? Well, if you have the image of the graph in your mind's eye, then it is obvious, right? Because this is the upper half of a horizontal parabola, right? The square root function, yes, that's sort of, you're familiar with that, right? 0, 0, 1, 1, 4, 2, and so forth. And it's because this is only positive outputs, right? The positive square root of x is the upper half of a horizontal parabola, and that will pass the horizontal line test. How do you find the inverse function for this one? Should we do that? Let's do that on pencil and paper. Can I get pencil and paper here? Yeah. Okay. So this is number 15. We have f of x equals the square root of x. So this is 1 to 1. How do we know? Well, suppose that square root of x1 equals square root of x2. If the outputs are equal, does that mean the inputs are equal? Yeah, not so obvious. And you kind of have to think about it logically. How is it possible that the positive square root of one number is equal to the positive square root of another number? That's only possible if the two numbers are equal, right? Now you might say, well, yeah, this is true if and only if the squares are equal, right? Sorry. Square of this equals the square of that. Are those equivalent statements? So this is going to say x1 equals x2 then, right? Yet, because these are positive numbers, if two positive numbers are equal, then their squares are equal, right? In fact, two positive numbers are equal if and only if their squares are equal. So the numbers have got to be the same. So the outputs are equal if and only if the inputs are equal. So what's the inverse function? So find a formula for the inverse function. So step 1 was to write y equals the square root of x. Step 2 is to solve for x. Well, here you have to be careful, right? How do you solve for x here? Well, x is going to be y squared, right? But that has got to be positive, right? X has got to be positive, and so y has got it. So this is positive as well, right? Y is positive. So now if you were to graph, so if you were to reverse the variable, step 3, and say y equals x squared, right? So rename the variables. Am I monitoring the chat? I'm not. You can just blurt out too. Okay. Or interject if you like. You don't have to blurt. You can just interrupt. You don't have to raise your hand. Okay, so if you reverse the variable, you get y equals x squared. Well, this is a parabola, but it's only the right side of the parabola because we said that x is positive, or we said that y is positive, and when you reverse the variables, that means that x is positive. And so here we're requiring that x is a positive number. So we're only getting the right side. So if we were to graph the function and its inverse, would we see that symmetry? You betcha. Let's take a look. So we're going to make a table of values for x and the square root of x, right? So 0, square root of 0 is 0. A quarter, the square root of a quarter is a half. 1, square root of 1. The positive square root of 1 is 1, right? 4, positive square root is 2, right? So then I'm going to make my graph. How are we doing? We got 9 minutes. Make my graph like so. And I'm going to use the same scale on both axes, right? Remember we said that was important to see the symmetry properly. So what scale? Well, I want to get up to 4, right? If I use inches, that's going to be a problem. Can I use centimeters instead? And say 2 centimeters is 1 unit. So here's 1, 2, 3, 4. Okay, on the y-axis. And horizontally, I've got 1, 2, 3, 4, 2 centimeters per unit, right? And so here is 0, 0. This is 1, right? So if I chop that into halves and then quarters, I can see a quarter goes to a half. The square root of a quarter is a half. Then this is 1, 1 here, and 4 gets mapped to 2. About there. So this is the upper half of a horizontal parabola. Right? This is our function. So we said the inverse function is, x squared, right? And I can get the table of values for the inverse function just by swapping the columns, right? So I'm just not even going to do computations. I'm going to say the square of a half is a quarter. Well, I guess I am kind of the square of 2 is 4. I mean, it's consistent with the computations. And so I want to get in there and plot those points. Okay, so here's 0, 0. Here is a quarter on the output, right? And there's a half, 1, 1. So they intersect there. And 2, 4 is up here. And I see the curve, the right side of this parabola, right? And where's the line of symmetry? Well, that's the line y equals x, right? I'm going to draw that in pencil because otherwise it'll be too much of a mess here. Does this work? Okay. And so this is a reflection across the line y equals x here. This, gets reflected to itself. And this is a reflection across the line y equals x up here, right? So that these two line segments have the same length. Yeah, it's got that symmetry. And ordinarily, y equals x squared would be both sides of the parabola. But if you're talking about the inverse function for the positive square root function, then you're talking about the part of the parabola y equals x squared, where x is strictly positive, because y is strictly positive on the inverse function. Everything is reversed, right? Input and output are reversed. So should we look at some exercises maybe? Let's go here and see what kind of exercises do we have for the inverse functions. Lots of them. 17, okay. So here we see circumference of a circle is a function of its radius given by C of R equals 2 pi R, my lord. That's how you remember the formula for the circumference of a circle. Well, you derive it from the fact that the pi is the ratio of arc length to central angle, right? Well, sorry, that's pi is the ratio of circumference to diameter, right? So the diameter is 2r, and so circumference, so if you take 2 pi r and divide it by 2r, which is the diameter, then you get pi. That's the definition of pi. And you remember this formula also because it's sung to the tune of Kumbaya. 2 pi r, my lord. Okay, that's memorable. How are we doing? All right. So express the radius of the circle as a function of its circumference. Okay, so let's do that. I'll go to my paper here. If I can find it. Finding my mouse is sometimes a bit of a chore. Where'd the mouse go? Okay, there it is. Okay, so we've got our function of r is, well, they're actually calling it C of r, so the name of the function is C. C is the first letter in the word circumference, and that's 2 pi r. So it's a linear function. It's actually a line through the origin with slope 2 pi. So its reflection is going to be a line through the origin with slope 1 over 2 pi. Let's see if that's true. So step 1 is to write, shall we? So we're used to x and y, right? And so now we have c and r instead. Is that okay? So I'm not going to write the function notation, and I'm going to use the output variable as just c. Okay? And so I'm conflating the name of the function with its output variable, which is a common thing to do. So sometimes we write y of x, and then we just write y for the output. Instead of y equals f of x, we just write y of x. So that's kind of what's happening here. You see, I wanted to write f of r. So c equals f of r, but they didn't do that. So let's go with what they're doing. So step 2 is to solve for the input variable in terms of the output. Or in other words, solve for r in terms of c. And that's easy to do, right? R is c divided by 2 pi. So the inverse function, f inverse of c, is equal to c over 2 pi. Right, so that gives us r, the radius of the circle, in terms of the circumference. And what you do is you take the circumference, divide it by 2 pi, and you got the radius. Would it make sense to switch c and r here? Well, it's problematic, isn't it? Because r represents radius and c represents circumference. So if I were to say c equals r over 2 pi, you might think, well, if the radius is r, then the circumference is r over 2 pi. But no, That's the inverse function. So, you know, if X and Y are just sort of abstractions, it's like what I said about cats and dogs, right? A dog is not a cat. So if you were to swap them, you'd still have dogs are dogs and cats are cats. So here, if we were to swap the variables, they would mean the opposite of what their letter represents. If it's just X and Y, then it doesn't really sort of represent the name of the thing so much as an abstraction. But here, R is radius and C is circumference, so it wouldn't make sense to swap them. Anyway, let's go back to the, unless you wanted to plot them in the same plane, right? In which case, yeah, you could do that. So, but here, what do they want? They want C divided by 2 pi, right? Okay, I'm gonna write C divided by, in parentheses, 2 pi. Yeah, it has a pretty type there, so that's what we want, right? So evaluate the function you found in part A. Notice that they have R of C, right? So they're not changing the names of the variables, right? So R of C is, if the circumference is 68 pi, then the radius is what? Well, you divide that by 2 pi and you get 34. Explain the meaning of the equation in part B in a complete sentence. Oh, great. This is like a little essay problem. So if we know the circumference C of a circle, we can recover the radius by dividing that circumference by 2 pi. 2 pi? Yeah, that's fine. You know, this doesn't get automatically graded, right? How are we doing? It's 12:11, which means we're out of time. So yeah, tomorrow we'll do more exercises out of the book and maybe look at some more of these. I wanted to sort of call this to your attention, get you started on it. Any questions before we quit? I think I'm expected in my office instantaneously through the magic of the internet. I will be transported. Okay. I'm going to stop the recording.